This is a brief demo of the EPLANT-Piping system. For more detailed information, go to the online EPLANT training platform. EPLANT-Piping is used to create a virtual 3D model of a plant from project specifications, and from there automatically generate piping isometrics, 2D drawings, and material requisitions. First, we'll look at the database module. We open a piping specification class, in our case the A1, and see how specifications interact with the dimensional catalog. EPLANT stores piping specifications in a DBF format file. We can load this table here or importing it from an Excel file. First we find the class name and next to it the component code, the main diameter range, secondary diameter range for reductions. The other columns are for specifying parameters associated in that diameter range, such as rating, schedule, main and secondary end code, material code, and other parameters. To understand the specification structure, we'll look to the component codes. Each EPLANT-Piping component is built from a code defined in this table. User can add new ones if required. Each code has a generic description associated to it, as well as several more parameters that define the behavior of that component. Let's go to the material codes now. First column defines the material code, and next the associated description that is used in reports. Let's look now at the end code, that defines what implicit elements are generated by each specific connection, if any, such as gasket and bolts, weldings, etc. Let's see now the relation between specifications and the dimensional catalog. In the project setup, we see that the default dimensional standard is defined. This standard is the name of a folder where the dimensional tables of each component of that specific standard are stored, but the class can specify explicitly another standard for a given component. We are going now to open the table that contains the face-to-face dimensions of a flange gate valve. Rating value is automatically derived from the specifications during the component placement. We'll start now working in the graphic module, here shown using ZWCAD, but EPLANT is also compatible with AutoCAD. We are going to create a model of a pump, selecting from a predefined parametric definition. We select here the basic pump type. This dialog box allows specifying all parameters of the selected equipment type. From this menu, we can also select a specific model. In this case, the equipment also defines nozzles. They can be modified after the generation as well. We assign now its name or tag that will be imported from the project PNIDs. And last, we define the equipment insertion point. With execute, the equipment will be generated. We can query any elements of the equipment to check for its name. In addition, each nozzle can be queried using the same command available for piping components. Equipments can be easily defined also from scratch. We continue now showing how to place a variety of piping components. We'll work in a 3D model with 120 piping lines. We can see the very small drawing file size. Projects with several thousand piping lines have been worked out with standard off-the-shelf PCs, a feat by far that no other plant design system can achieve. We are going to connect a piping line to an existing equipment nozzle, first by placing a slip-on flange. In case of connecting to a nozzle, we need to select the working line. We place now a 100 mm pipe segment. Component selection is always generic, and its characteristics such as piping class and diameter are derived from the very selection. We continue with an eccentric reduction. Now get valve that will be placed at a given distance on the piping axis. Being a component with tag definition, can import and validate tags defined in the project PNIDs. The piping path will be defined placing elbows at every direction change. Each reference can be a given distance or derived by snapping to a connection point of another component or a plain AutoCAD snap. And to finish, we'll automatically place any missing flange and pipe segments. Looking now at the piping specification definition in the database module, we can see how an 8-inch elbow is specified and verify that these parameters are the same of the elbow placed in the 3D model. We are going to show now how to automatically generate piping isometrics from the 3D model. First of all, let's check the connectivity of the line. Connectivity is correct, and we can verify if this line is connected to other lines or nozzles. We can now extract the isometric right away. The isometric will be divided in 2 sheets. This is the first sheet, and we can see the continuation node to the second sheet. Contrary to other systems, EPLANT generates intelligent isometrics, that is, with the same information built in 3D models. It is possible to add new nodes, for example, placing a bob elevation, and rebuild any additional information such as the material takeoff, where we are changing now pipe lengths from spools to total. The MTO format can also be easily changed, for example, to add a custom code. 2D plans are generated attaching all relevant 3D models as XREF and then creating views with this command. Each view corresponds to a prism that filters the volume to process, links the view to a viewport in Paperspace, and sets what to do. The projected elements retain the 3D model data and can be dimensioned and annotated in Paperspace. Other options are available, such as to automatically place nodes, to update nodes if 3D model change, and node format settings. To finish, we'll take a look to how generate material reports from the database module. Each data has a specific table where all 3D models are consolidated. Here is the piping table. From the report option, several formats are already defined. Each report can be generated either to a text file or to an XLS file, as in our example. We can also modify its format and look to a preview. And now we generate the report. With the same logic, we can generate the line list, the equipment list, the nozzle list, and all the reference data, such as specifications. Much more details can be found in the free online training tutorials.